Phase diagrams. So a phase diagram is a map of the state of a substance as a function of pressure and temperature. By phase, we mean state. So there's 3 phases of matter, 3 states of matter: gas, liquid, solid. So we have a map with pressure on the y-axis, temperature on the x-axis. I'm just going to show you one real quick. So this is what we're talking about. Here we have pressure and temperature, and then we have these lines that separate the 3 different states: solid, liquid, and gas. So these different regions represent conditions where that state is stable. The lines or curves that separate them represent a set of temperatures and pressures under which those 2 states are in equilibrium. And they're named in terms of that transition. So we have a vaporization curve, a sublimation curve, and a fusion curve. And then we also generally identify the triple point, and that's a unique set of conditions at which all 3 states are stable and in equilibrium. Now that's different than a supercritical fluid. At a triple point, you have the solid, the liquid, and the gas in equilibrium all together. Supercritical fluid is where the gas and the liquid have kind of merged to be the same thing. They're not both present. Okay, so here we have our graph. This is for water. And so this darker blue area represents conditions under which water is a solid. Lighter blue, a liquid, and the lightest, almost gray here, is where it's a gas. So if we look at 760 torr, which is normal atmospheric pressure, and we come across here as temperature increases, we see that there is a line here, the fusion curve, between the solid and the liquid at 0 degrees Celsius. At 0 degrees Celsius, the melting point of water, you have equilibrium between solid and liquid, and that's what this represents. If you continue going higher in temperature, you get to the vaporization curve, where you have the equilibrium between liquid and gas. That's the boiling point. Okay? The triple point is right here, where you have equilibrium with all 3 states. And up here at the end of the vaporization curve is the critical point. Beyond the critical point, there's no separation between liquid and gas. You have a supercritical fluid. Any questions yet? So you should be able to look at an unlabeled graph that doesn't have sublimation curve, liquid, solid, etc. on there, and you should be able to identify what those different regions are. A phase diagram is helpful because we can predict what's going to happen to this substance when we change temperature and or pressure. And so we call this navigation within a phase diagram. So you can look at a horizontal line or a vertical line. So if we look at this horizontal line A, this is a pressure of 1 atmosphere. If we start down here at minus 25 degrees Celsius and we increase the temperature, keeping the pressure constant, we see that we'll get to a point where the water melts, the ice melts into a liquid, and if we continue going on, the liquid gets warmer and warmer and warmer, and here it'll boil. We can also look at what happens if we change the pressure and keep the temperature constant. So if we take start up here, 1 atmosphere and room temperature of 25 degrees Celsius, and we decrease the pressure, and we decrease the pressure, and we decrease the pressure, at 25 degrees Celsius, we can get water to boil. But it has to be at a very low pressure. And this is what my high school chemistry teacher did. He pulled a vacuum on a big flask of water, and it started to boil just sitting on the counter, and he made us all come up and touch it. And of course the first person was like terrified. You're going to make me put my hand on a flask of boiling water? It was room temperature, and it was boiling. It was the trippiest thing. I mean, there's a lot of stuff I don't remember from high school, which is probably a good thing. But that's one of these clear things. I can even see the bench, the orientation in the class, touching that flask of boiling water at room temperature. Very, very neat. How come we don't do that one? Because don't have a pump that'll pull a good enough vacuum. It's a bummer. That's something I really want to be able to do. Phase diagrams for different substances are going to have a different appearance. Look at the slope of this fusion curve. For iodine, this has a positive slope. For carbon dioxide, it also has a positive slope, but it's closer to vertical. If we go back and look at water, water's fusion curve slopes the other way. That's weird. Most substances do not act like this. With water, if you
Increase pressure?
yeah, if you take a constant temperature and you increase the pressure, you actually cause the ice to melt. That's not the case for things like iodine. Here, if you increase the pressure, you're going to cause the liquid to freeze, not the other way around. So that's a weird thing about water. Interesting thing about carbon dioxide, here's the triple point. The triple point occurs at 5.1 atmospheres. You cannot have liquid carbon dioxide below 5.1 atmospheres of pressure. That's why dry ice doesn't melt, it just sublimes. So down here at 1 atmosphere of pressure, it just goes directly from the solid to the gas.